Thank you. This is a joint work with Eric Friedman and Alex Psomas from Berkeley. So I want to talk about multi-resource fair division, and in this setting we have multiple resources. In this talk I'm just going to focus on 2 resources, CPU and RAM. And in this setting, agents are going to arrive, and they're going to have normalized demand vectors. And just think of the demand vectors as an agent coming and saying, I want to use your resources, and for every unit of CPU that I get, I want half a unit of RAM. So in some sense, it doesn't matter how much they say. So if an agent comes and says, I want 100 units of CPU and 50 units of RAM, that's because we're considering just fairness. It's the same as saying I want 1 unit of CPU and half a unit of RAM, so we're just going to normalize that. And we're going to assume these preferences are Leontief or the Leontief utilities, which essentially means that if my demand vector is 1/2, which means I want 1 unit of CPU and half a unit of RAM, I get the same utility if I get half a unit of CPU and a quarter unit of RAM as if I get half a unit of CPU and half a unit of RAM. So I don't get any extra utility from this resource I don't need, in some sense. And very hand-wavily, we want to allocate as much resource as we can all the time, because essentially this is a problem motivated on the systems world where you actually allocate resources, and if there's one thing systems people hate more than anything else, it's that resources are idle. So essentially idle resources are wasteful, and we like to allocate as much of the resources as possible all the time, and we'd like to do this in a way that's fair. So what do I mean by fair? Put aside the word dynamic for a second and just let's think of multi-resource fair division. So actually, Nikhil talked about one notion of fairness, which is the Nash bargaining. But we're looking at another notion of fairness that's become quite popular in the past few years, which is dominant resource fairness. And it's quite simple. Essentially, all it means is we want to equalize the allocations with respect to the dominant resource. So let's just take a look at an example. We have 3 agents. The first one has demand vector 1/2. The second one wants the CPU and RAM with, in equal amounts. And the last one only wants RAM. So the DRF allocation is going to be this one. And you can see that it seems correct because it allocates 2/5 of the dominant resource to each agent. Right? So for the middle agent, we could think of either the CPU or the RAM as the dominant resource. It doesn't make a difference. So I'm not going to tell you exactly how you compute this DRF, but this allocation. But I urge you. So the concept of DRF, this notion was, like I said, introduced by Godse et al. In 2011. And if you're interested in it, I strongly urge you just to read the paper by David Parks, Ariel Prokacha, and Nisarg Shah, in which they give a cleaner definition, a very clean algorithm that shows how to get this allocation. So DRF has some nice properties. It's NV-free, it's Pareto-optimal, it's strategy-proof, but the main reason we focus on DRF and not, say, Nash bargaining solution is because a lot of systems people have been adopting it. So because this paper actually has a motivation from the systems world, we use the notion of fairness that systems people like. Okay, so now let's move on to dynamic DRF. And essentially, I've shown you that there's always a DRF solution, or implied there's always a DRF solution. So there's always a DRF solution. And if we look at the agents arriving online, the first agent arrives, and we can just do the DRF solution. So the first agent arrives, and we do this allocation, which is optimal. And then the second agent arrives, and again, we just allocate them half to their dominant resource. And the third agent arrives, and again, we can just execute this DRF algorithm and find the optimal solution, which is the same solution we just saw. So what's the problem? Right? So essentially, you could think of dynamic DRF as solved because at every iteration, we can just apply the offline solution or the static solution. But this is a quote from a paper by Godse et al. That is about a slightly different problem, but it applies just as much to our problem. The offline scheduler is just not applicable. Because if we called it every time a resource freed up, or in our case, every time an agent arrives, essentially we'd just be reallocating a lot. And if there's one thing systems people hate almost as much as the resources being idle, it's reallocation. Because reallocation is expensive. And just think about a machine running 1,000 programs at the same time, and now an agent comes and we want to reallocate. So essentially you have to stop 1,000 programs from running, reallocate resources, start them again, hopefully from the place where they stopped last time, right? So this is really expensive, and systems people basically hate this. So if we don't want to reallocate, there's actually a really nice work by in Ariel Prokacha and Nisarg Shah, which discusses dynamic fair division, and in particular dynamic DRF, when we don't reallocate. So there are problems that arise there. So NV freeness becomes complicated, and they address these notions. But the important thing from our perspective is that because they don't reallocate, because they don't use any reallocation, this is impractical. And the reason is that machines can be mostly idle. So when the first agent arrives, if you know you're never going to reallocate, you can give them a very small fraction of the resource, right? And essentially, if no one comes for a long time, basically you have a machine that's almost completely idle. So we're stuck in a situation where, no reallocation is wasteful or completely impractical because machines are idle. Unlimited reallocation is also impractical. So what can we do? Well, obviously restrict the amount of allocation. So we propose this something called a control vector, which is just a vector that says how many users I'm allowed to disrupt or interrupt whenever an agent arrives. So for example, the control vector, which we know by psi, could be this, 0, 1, 0, 2. And this just means when the second agent arrives, I'm allowed to disrupt the first agent. When the third agent arrives, I'm not allowed to disrupt anyone. When the fourth agent arrives, I'm allowed to disrupt either of 2 of the first 3 agents that are there. And if the length of the control vector is 4, this assumes that there's going to be at most 4 agents in the system. And notice that the first coordinate here is 0. It doesn't really matter what the first coordinate is, because when the first agent arrives, there's no one there to disrupt. But we make it of length n, so that when the ith agent arrives, that corresponds to the ith coordinate. So that's just for readability. And just a small note, which I had to write this because I probably say it, we call this, whenever a user is disrupted, we just call him a donor for that round. Okay, so why is this control vector a good idea? Well, the idea is that it's an abstraction that captures a lot of reasonable scenarios. So for example, if the control vector is just a vector of d's, you could think of this as whenever an agent arrives, we can interrupt d users. In particular, when d is 1, we can think of it whenever an agent arrives, we can interrupt 1 user. And this was actually the subject of our paper from 2 years ago. But there we only considered a single resource. And it also takes into account situations like this, where you have the control vector, which is 0, 0, 1, 0, 0, 1, or something like this. And that kind of means that you can interrupt one user one user every 3 arrivals. And this was actually the original motivation for this paper, because after EC 2 years ago, we went to some systems people who suggested this problem to us and said, we solved this problem. We didn't call it a control vector, but we said, we can handle a situation whenever, no matter how many people are in the system, whenever anyone arrives, we only have to interrupt one person. And they said, okay, so that means if 1,000 people arrive, you have to have 1,000 interruptions. And that's completely impractical as well. So, okay, so we thought our solution was pretty good, but apparently it's still not very good. So back to the drawing board. And then that's why we thought about handling situations like this. And because we can handle arbitrary control vectors, we can also handle control vectors that kind of encodes system-specific requirements. And ideally also control vectors that are revealed online. So the system doesn't even have to decide, but at some point the system says, oh, you know what? I can now reallocate 2, so I'm going to give you a 2 there. Okay, so our algorithmic goal, we get as an input a control vector that could be infinite. and agent demands. And these could be either arriving online or known ahead of time. Of course, we'd prefer it if both of them are just revealed online. That would be a better algorithm. And our output is for every agent an allocation. So overall, a set of allocations that are fair. So I told you what I mean by fair in the static setting, but I can't be completely fair in the dynamic setting. I can't. If I restrict these allocations, I can't get this DRF, right? So what do I want to get? Well, let's look at an example, and that'll help me explain exactly what I mean. So our control vector is 1, 1, 1. We know there's going to be 3 agents in the system. The first agent arrives, only wants CPU, so we can give him all the CPU. And the second agent arrives, and it just wants RAM. So now if we give it all of the RAM, and the third agent wants both of them, we're stuck, right? Because we can only have one donor. And then we have to choose if we allocate from the hedgehog or from the rabbit. So we have to leave some left over. And then say we give the rabbit 2/3, and then the third agent comes and indeed he requires 1, 1. So now we are able to satisfy this agent by letting the hedgehog be the donor and leaving the rabbit's allocation as it was. Okay, so then we can get something like this. So how good is this? How good is this fair? Is this a good allocation? So the fairness measure we propose is this. The fairness of a specific stage is the minimal share divided by the DRF share. And that's basically, the DRF share is the best thing we could hope for under this measure of fairness. So basically we say we want the smallest share to be not too far from the best thing we could have hoped for every stage. And over the whole, and the fairness ratio of the whole algorithm is just the minimal fairness over all stages. So I claim this is kind of a strong notion of fairness. And again, this is debatable, but essentially we're saying the worst case over all stages, the smallest share is still not going to be that bad. So again, the algorithmic goal now, slightly more formally, is we would like to output a set of allocations which have a good fairness ratio. So I'm going to give you upper bound or low bound, or actually an impossibility result and an algorithmic result, because the upper bound and lower bound are switched here. But before that, which control vectors can we handle? So ideally, we'd like to have just adversarial control vectors, right? But we can't expect to handle just completely adversarial control vectors, because if you're the adversary, what would you give us? Well, you just give us a vector of all zeros, so I'm not allowed to reallocate ever. Okay, so we do want to give the adversary a lot of power, but we do give him one restriction, in that they're allowed to choose any control vector they want, subject to there being no more than C zeros in a row. So there are at most C stages in a row in which we're not allowed to reallocate at all. And ideally, our fairness will just be a function of this C. Okay, so I'm going to give you an upper bound and a lower bound, and we're going to look at a really simple setting. So there's 2 resources, like we said before. Agents are only going to be allowed to have binary demands. So they either want only CPU or only RAM, or both of them in equal proportions. And in this case, if you notice, DRF is just the most demanded, 1 over the most demanded resource. 5 people want CPU, 4 people want RAM. The best we can hope for is give each one a 5th. The control vector is the all one vector, and the demands are revealed online. Okay, so let's look at the impossibility result. We're going to have the same example we had before, and actually the same algorithm and the same allocation. So in the first stage, the hedgehog comes, we give him 1. What's the fairness of this stage? Well, the best thing he could have hoped for is 1. He got 1, fairness is 1. Second stage, we gave the rabbit 2/3. Best he could have hoped for is 1. Right? We could have given him 1 and the hedgehog 1, but we gave him 2/3. So the fairness is 2/3 over 1, which is 2/3. And in the third stage, we gave the duck 1/3, which is the minimum share. Ideally, we could have given him half. Right? We could have given the hedgehog, the bunny, and the duck half, but we gave him 1/3, so the fairness is 1/3 over half, which is 2/3. So overall, the fairness ratio of this algorithm is 2/3 in the second stage, and in the third stage, it was 2/3. And I claim that this is optimal. I'm not going to prove that it's optimal. I think you can maybe kind of see or kind of say, kind of be convinced that it's optimal, but I'm not going to prove it. So we do prove it in the paper. So this is 2/3 is the best we can hope for. Now let me give you an algorithm that does not achieve 2/3 and is provably not the best thing that we can have. Unfortunately, we don't know what the best thing we can have is, but we do have this nice algorithm, so let me give this. So in this algorithm, we're just going to decouple the resources. And each resource is going to keep a list of the agents allocated to it, sorted by allocation. When a resource is demanded, it tries to allocate the top agent. So if an agent arrives and just wants CPU, the CPU allocates the top agent. From the top agent. If an agent comes and just wants RAM, the RAM allocates just from top agent. If an agent comes and wants both of them try to allocate. If there's no conflict, fine. That is the donor. If there's a conflict, we have a token, and the one holding the token gets to choose who allocates. And how much do they allocate? So they allocate sigma, for some sigma, which I'll talk about in a second, that keeps it feasible, and they're just going to allocate sigma over the DRF allocation. So let's look at an example. The allocation looks something like this. At some point, the RAM has a token, the chicken comes, he wants only RAM, so the RAM would like to allocate from the goat, so he does. And because there's now 4 agents in the system, or 4 agents on the RAM, he just allocates sigma over 4 to the chicken and to the goat. And then a rabbit comes and wants 1-1. So now there's a conflict, right? RAM wants to allocate from the bird, and the CPU wants to allocate from the koala, but RAM has a token, so we allocate from the bird, and we give the bird and the rabbit sigma over 5. And the token moves over to the koala. Okay, so this is the algorithm. And it's so as long as sigma, whatever sigma we choose, makes sure that this stays feasible. In other words, that we never allocate more than 1, this is a good sigma, right? But how do we know what this sigma is? So we could think of this algorithm as both resources generating a control vector with at most 1 consecutive 0 at each one. So if we take sigma to be the best fairness ratio for this case, for the single resource case, with an adversarial control vector that has at most 1, 0, that works. Maybe you're convinced, maybe you're not. I don't have time to go into to explain further why this works, but hopefully you kind of have some intuition of why this probably works. And in the paper, we give an optimal algorithm for the single resource case. And we show how to compute the sigma. And actually, that's the main technical result of the paper, is showing how to compute the fairness for an adversarial control vector. So the main theorem is, or one of the main theorems is, there's an instance optimal algorithm, meaning for every instance, every control vector you give me, it's optimal for that. Whose fairness is this function, which is a harmonic function, which h is a harmonic number, for any control vector that has at most c consecutive zeros. And just so you get some idea of what what the fairness ratio is, so if we're allowed 10 consecutive zeros, the fairness is going to be about 0.3. And if we're allowed 10,000 consecutive zeros, the fairness is still pretty good, right? So you can still get a tenth of the fairness, even if your control vector is 10,000 zeros 1, 10,000 zeros 1. And for c equals 1, we actually get an exact bound, not just a tight bound. So plugging this in, this gives us an algorithm that gets a fairness ratio of 0.6068 in this setting. So to summarize, we discussed dynamic fairness in the single resource and multi-resource case, introduce this concept of a control vector. We show an optimal algorithm for a single resource and show how to compute its fairness ratio. And we show a lower bound and an upper bound, or an impossibility result. And the possibility result, in the paper we show actually a stronger impossibility result with very different technique. And this leaves a lot of open questions. And especially, so the most interesting, from my perspective, is essentially we don't really know anything, or we don't know enough about the multi-resource case. So even for this very, very simple case that I showed you, really simple control vector, binary demand vectors, the control vector is known in advance, even if the binary demands, even if the demands are known in advance, we still don't have an optimal algorithm. And of course, we'd like to extend this to arbitrary control vectors and arbitrary demands. And I haven't said anything about departures. And another extension is to other notions of fairness. So I wrote competitive equilibrium from equal incomes, which is essentially what Nikhil was speaking about. So there's other notion of fairness that may be just as reasonable, to which we should extend this. Thank you.